All right, so let's now look at how we can apply calculus into parametric equations. So I have to mention one thing, that the lesson here at first was initially planned to be only delivered for the calculus level students. However, as I was going through and really getting the lesson plan itself prepared, I decided to put more details into the lesson plan so that the first half of the lesson, basically the first part of this video lecture right here, can be also used and can also be learned by the students at the pre-calculus level. And so the first half of the video lesson here can be used for either the calculus students or the pre-calculus students to be learned. Okay, so here we go. Let's get into what parametric equations here. So the first half of our lesson here is to really have an in-depth look at what it means by being a parametric equations. And then, of course, even though I try to be as in-depth as I can, but of course there are certain further details that you need to definitely wait until you actually being enrolled into either a beginning physics course or a Calc 3 level to really have all that detailed understandings put together. But here I guarantee that you will be having a clear enough understanding so that when we actually apply the calculus work into your parametric equations, then you will feel comfortable with that. Okay, and so here we are. We are now about to learn what parametric equations are and how, in the later part of the lesson, how we can apply calculus into working with parametric equations. Okay, so all right, so now to get started with the idea over here about what parametric equations are, then now I'm just simply going to, and you don't need to ask me why I named the variables like what I'm about to do here, but let's just simply, I am going to define, okay, right at start I am going to define x here. It's a lowercase letter x, so you might think it's just the usual letter x. Okay, whatever it can be, it is a variable, but I'm defining it, that x variable here, as a function of t here. And let's say I want x of t as a function. So instead of the usual f of t, g of t, there is a reason why I'm naming that my function here x of t here. Okay, and if you have a curiosity or a question wondering why I named the x here, you will find your answer later. But here, x of t as a function in terms of the t variable. So t variable here is the dependent variable. This is our independence variable. And so here I'm looking at 5 minus 4t. Okay, so it's just a linear function as usual. Okay, and I am going to define another function where I call that, and a function itself is a variable as you have learned up to this point. And so y variable, but now I define it as a function t right here. And that function here, let's say my definition for this function of t is how about 2 plus t. Okay, and so now at this point we are at the very first step into looking at parametric equations. Either you are at a calculus student, you're at a calculus level, or you're at a pre-calculus level. Let's just pretend that this is the first time ever you are looking at what parametric equations are about. So we always going to begin by just simply, and it's my style here, I begin by just simply define two separate functions, and I want my viewers to only see these two as two separate functions. And again, there's a reason why I didn't name these as f or g or h, the usual functions naming. Now instead I name my variable here x, lowercase letter x, and here's lowercase letter y. So I have two separate functions. So these two are not necessarily related. The two functions here are not necessarily related. They're just any two functions. And they're both functions dependent on the t variable. Okay? So this is now, once we have had the two functions here defined here with the input and with the variable t here being the independence variable, and now this is the next thing we can do, just like how we operate with functions. Then Now think about, you roll back to the time that we've learned about function on its own, then the usual work, the very common work here is to construct tables. But now our table of values here is going to grow into 3 separate columns. I am going to be using one column for my t variable, my t independence variable, and we can choose a few values, let's say -2, and then the -1, and then 0 and 1 and 2, for example. Okay, so the t variable here is the independence variable, so we have our choice, and like I said, it's independent, so we can pick it anyhow we want, but make sure we put them in increasing order top down to the list, or the decreasing order from the top down. Okay, but we definitely need to put the values of our independence variable in a certain order. And now once we have chosen the values for our independent variable, then we already knew that the only extra thing is now we're going to have 2 other columns of values are being dependent on these chosen values of t right here. So if when t equals -2, then our x value here, our x values, the function output value for x is going to be, that is going to make it 13, positive 13. Okay, as the calculation here says, -4 times the input t. The input's now currently being -2, so -4 times -2 is making it positive 8 plus 5. Now I have a 13. And then in the meanwhile, at the same time, on the other function, for the function y right here, so these two are having nothing to do with each other. I don't need any, and I really don't see how these two are related at all. They are just 2 functions, and we just try to put them all in one table. So one set of t values, and now we can come out with 2 set of outputs from 2 separate functions, completely 2 separate, nothing to do with each other. Okay, and so here, so that means at this point right here, my value for y here is going to be 0. Okay, because -2 being substituted into our function, 2 plus and -2 is a 0. So just like that, now viewers can go ahead and start independently calculate these corresponding value for x and y on each of these other t values. So, and I'll also be doing that the same as well here. So when t is -1, then we're looking at 9, and that's positive 1 for y. When t is equal to 0 on my table, then my x value here is going to be 5, and my y value here is going, based on this function definition here, then my y value is going to be 2. And when t equals 1, then my x value is going to be the 1, and my y value here, my row is a little tight in space right here, so I apologize for that if it caused any inconvenience or hard to see anything like that. But when t equals 1, my y value here, 2 plus 1 is 3, and when my t value equals 2, then I'm looking at -3 for x, and we're looking at 4 for y. Okay, so that's my table value. So just a little bit more than the usual way. That's one column for the independent variable, but we now can produce 2 parallel. Okay, I would say parallel because I just want to say that we can get these things at parallel time, but I don't aim to see any relationship between x and y at all. Okay, but so now see, at the same time, the one t value can give me 2 different values because they came out from 2 functions. So nothing violating our understandings of functions so far. Okay, and so now I am going to have a plot of these. So as I said in before, I don't need x and y to be related. But now here's how I see it. The whole idea about graphing is that when we are looking at a graphing system, x and y, and now x is the values we place on a horizontal axis, and y is the axis for all the, the y values are being placed on the horizontal axis right here. But so now when I draw this graphing space right here, I don't need anyone to see this as I'm getting ready to draw a function. Nope. I want my viewers to start seeing this graphing space here as a map. Okay, it's just a map. So if we pick a point here, the idea of graphing is any point here has horizontal coordinates and vertical coordinates. And conventionally, we're writing that as a pair of value x comma y. X comma y. And so in that way now, so that's just a reinforcement of your understanding from the very first day you are being exposed to the idea of graphing, which is whatever we call the x value, we're going to put, and together with the y value, we put that as a pair of value, and that's become a plotted point on the plane. But now that point here, we simply want to see that as simply a pointer on the map. Let's say home is a location, has coordinates 0, 0. Coordinates, and I'm now also using that term somewhere here and there as maybe as we work too far into math and we got exposed too far into the idea of function and we starting to forget about these. But x and y, we in the other names we call them, they are the coordinates of a point, a position, a location on a point, on a map. Okay, so I just want any one of my viewers to see this whole graphing space here as a map. So any point is a pair of values, and we treat that pair of values as a coordinates pair. Okay, and so now after we reinforce that idea, then why don't we, even though, yes, as I said earlier, and I never lied about this, I don't need x and y to have any relationship. I don't need, they could, but I don't need right now. I don't need to look for what that relationship is. I just simply see that as, hey, let's take this pair of value x for being 13 and y being 0. And let's take that pair of value and put that on the graphing plane, for example. So now my graphing plane that I drew on the other board is a little off scale. So why don't we turn over to my computer screen here, and then let's have a look at that. Okay, so all right, so that is our actual first point right here. So 13 comma 0, it's just as usual. Okay, and so just like that, on our table of values, the first pair here, when t equals -2, we come up with a pair of x and y. 13 being x, 0 is the value for y. But now we purposely put that as a pair of value, and so now that's how we came up to the graph as being plotted. Okay, so go ahead and have a closer look at our table because I am going to plot the rest of these points right here. So we are, and one more time, you can see that when I was showing the graph earlier on the computer screen, the horizontal axis was already reserved for the values of x. The y coordinates was already reserved. The vertical axis, the y-axis, was already reserved for the y values. There's no axis here that's reserved for the t. So when we are plotting these points, that's why, of course, they are just simply a point that came out from x value and y value, but there's no axis for the t. And so now, let me put the arrows on. Okay, but so here's the thing. So now I can see that you have to keep in the back of your mind, we come out with this point here, 13 comma 0, that's when t equals -2. Okay, and so now I am going to plot the next point right here. The next point we have is -1. That's when t equals 1. So when t equals 1, we have this point, and that should be 9 comma 1, and that is just perfectly consistent with our table of values that we've had. Okay, and so now look at how so think of each point here as just simply a point, a position on the map. And so when t was equal to -2, then we got a point, we stay at a position at 13 comma 0. And then when t changed to -1, then our point here, or think about we change to a different position, being 9, 1. Okay? And then so far there are only 2 points so far, so it's not much to tell anything about the story. But let's continue further into our table of values. So now, let's say when t equals 0, this third point that just popped out over here is when t equal to 0. And that is equivalent to our third pair of value right here, being 5, 2. Okay, so now let's continue further right here. All right, so our first point when t equals -2, we're looking at this point here. That point, and then we have that here, and then we have this here. Okay, so this is when t equals -2, this is when t equals -1, and this is when t equals 0. And so now, let's try again. Let's try another one. So when t equals +1, let's find out what happens. Our x value is 1 and our y value is 3. So 1, 3, we have another point right here. But so now after putting those 4 points together, we start recognizing, you see, looking at the trace of how these points are going right here. They leave behind a trace. All these points together make up a trace. And so now we start seeing that these points right here form into a path. Okay? These points form into a path. And so now let's try it one more. Let's put in one more value right here. So what about when t equals 2? And we have another point. So 5 points all together so far. And that creates so far it looks like it creates a path. And so now people viewing this, we're gonna start recognizing these points are making up a trace, a path that looks like so far. I'm not saying anything about a hard rule or anything, but seems like all these points are lining up into a line right there. Okay, and so it looks like that so far. It looks like that, and that's all we recognize. See, from the left to the right or from the right to the left. But basically, this is a path. All I want viewers to see here, this is a path from the first t value that we looked at, and then so on and so on and so on. And then on this path right here, our points are moving in that direction. So we got to think about, we pretend that we have some kind of motion here. Okay? And so now, let me prepare my computer screen a little further. All right, so now, what do we realize from this? And so, the way how I see that now is that now we can pretend, and after you've seen that demonstration, then now we can see, leave me a minute or so to erase the board. And so what was happening there is that on the x and y plane, now any point now, instead of being regarded as a point on the function, I don't need to worry about that, but any point on a plane is made up of 2 values as a pair of coordinates, x and y. But now each one of the x and y here is a function. Each one of the x and y is a value that's driven by the t variable. So now the t variable here is being referred to as, is now called, the t variable is called the parameter. Okay. Yes, it is in its truest sense. It is an independent variable. And both of our x and y coordinates on the plane, on the map, are 2 separate functions dependent on t. Okay? But now in a more advanced form, in a more formal term, t is now being referred to as the parameter of these 2 x and y coordinates. So it's in the end, we're starting to come back to what we've been learning. It's x and y. The reason now I name, back to if anyone was curious earlier, why did I name these 2 functions, x and y? Because I purposely want to show that eventually, even though at first they simply just any two functions dependent on t, but in the end, the x values for any point can also be a value dependent on t. And the y value, the y coordinates of any mapping point on the plane can be a function of t as well. So now both x and y coordinates of any point on the map, on the plane, it can be functions of the parameter t here. So t here is the independence variable, or now we call that the parameter. And then depending on where t is, but keep in mind, as the way how I was showing that on the computer graphing space earlier, then we don't really have an axis for t. But we just have to understand that as t changes, right, at different instants of t right here, at different values of t, we're gonna run into different pairs of coordinates value. Okay, and so now let's look at so now we understand that t is called a parameter, and so after seeing the plots here, how I put all the plots together. So now here's generally regarding. This is a general way how we can regard to this. Any point in general. I should have started out this way. Just any coordinate pair. Any coordinate pair, as we already knew, is a point on the map, is a point on the graphing space. But now if we treat each one of these coordinate value as a function, both dependent on t right here, then now generally speaking, these two functions together making up a point, but now it's not simply just a point, it's now the pair of x of f, the function x of t and y of t together as a pair. We refer to this as, this is the position. Okay, think about, we have a position, we have a particle that's moving on a path. So the path, I mean, it's just a shape right here, but we can have a particle that starts here at some time. Okay, when you saw it in the graph right here, when time was, and when t was -2, then we have a position here, and then when t is -1, and we switch to a different position, and then when t is at 0, we switch to a different position. So think about together, it describes the motion of sort of like a particle. Okay, and so now back to what I was in the middle of saying. Now when we put the x function and the y function here together as a pair of coordinates, then it generally describes this pair of x of t function comma y of t function. It generally describes the position of a particle. Okay, at the value at the parameter at some parameter t. Okay, and so now you might have noticed I accidentally set time a couple times, but you see the parameter t here, as a general understanding, it's a parameter, but it doesn't always represent time, even though admittedly time is one fundamental variable that's driving a lot of quantities out there, that's responsible for the change of a lot of quantities out there. But keep in mind, time is not the only the parameter that we can use. So generally speaking, now we can just simply think about what I was describing there earlier as we have a particle, and that particle changes its position. So this is the position at anywhere. Okay, the position anywhere of the particle, of any particle at some parameter value t right there. Okay, and that's the whole idea we understand about how each of these x and y coordinates can be expressed as two functions, but dependent on a common parameter t right here, or another way of seeing it's one common independent variable, but responsible for the changes in values of x and y in your plane right there. Okay, and so now in that way, how I see it, then back to these two right here, x is the x variable of the position of the point at anywhere, at any time, at any parameter t, and then y is also the y value of your position. But now together, these two equations, now we refer to them as the parametric. These two equations are parametric equations. And so, parametric equations. Okay, and to be precise, we can just say parametric equations of a coordinate pair of coordinates pair x comma y right there. So this idea we learned in this lesson is limited to only two coordinates right here, because so far, even up to the end of Calc 3, students only learn graphing space with two coordinates values, x and y. And so think about if you're on a 2D map right there. If you're on a map, then you just simply need to know your horizontal coordinates and vertical coordinates. But you don't need to know, but this idea, once you understand that, then one day when you arrive at the Calc 4 level, at the Calculus 4, where we start bringing in the 3D stuff, then your parametric equation will involve the third component. And when you get into a more advanced course, then your parametric equation will even involve more dimensions than that. Okay? And so now usually throughout this lesson, then when we talked about parametric equations, then it come in pair. These parametric equations will always come in pair. But just be aware that after this class right here, when you advance to starting at about the Calculus 4 or even higher than that, then parametric equation can come as a whole set, as an entire set of parametric equations. Okay, and so now let me even explain a little more about why is it important to describe, why is it important to, why do we have to bother describing a point, a pair of value is 13, 0, it's just fine, 9, 1, it's just fine. We have the functional notation that relates between x and y before that we've learned. It's just fine. Why do we have to bother express each one of these as a function of t right here? And what's useful about that? Okay, and so now let me prepare my computer screen a little bit. And then I will do another demonstration still on the same pair of parametric equations that we have here. So, all right, so here we go. So now back on my computer screen that I was showing earlier. So the first point was here for x equals 13 and y equals 0. Okay, and we have already seen that when I was doing the table of values and purposely put the t values in order. So I started out with t equals -2, then t equals -1. Okay, then we have another point. Then we jump to when t equals 0, then we had another point. And so after about 3 points and 4 points, we start recognizing that these points, so if we look back at what we have seen earlier, then we start recognizing after about 3 or 4 points a path. Okay, and so see, when t equals 1, we're looking at a value, a pair of value 1 for x, 3 for y. And when t equals 0, it was 5 for x, 2 for y. And so t is the parameter value, but then as the parameter value changes, it's responsible for different x and y pair of values right there. And so now 2, when t equals 2, then we have x equals -3 and y equals 4. So all that, now it shouldn't be a surprise anymore. And so just like that, now if I put on the actual prediction of the path that these points are going, see, because in the end I've only constructed 5 points so far. Okay, so in my table of values, there are only 5 points so far. But now it looks like all 5 points are perfectly on this line right here. And please do not worry about, is this line, what's the slope, and y equals mx plus b. We don't need to worry about that anymore. We want to see this line as a path, as a physical shape right here. Okay, and so now back to what I was trying to say earlier. I was trying to trigger your understanding of, so a line is a line. We have been just fine with y equals mx plus b. Why do we even bother, expressing x as a function of t and y as a function of t, and these two are supposedly independent from each other. They're only dependent on the t variable. And why do we have to go through so much and build a 3 columns table and all that? Okay, because in the end the line is just a line. Why do we have to bother? But here's the reason why. So a path is a path. But now, as we understand that these points are lining up and following the path, and here's the thing. As I keep putting more points, so far I'm rolling back to the point where we had only 2 points here on the plane. But now as I add to another point right here, and that's simply just when t goes to 0. So I started out with t equals -2. Then I came to t equals -1. Then I came to t equals 0. This is where I got that point. Okay, and then as I keep putting in more t, okay, so t equals 1. This is my next point. So now I'm going to even keep putting it forward. When t equals 2, I have another point. When t equals 3, I have another point. So now the benefit of using, and now let me put that in a further zoom here. The benefit of using parametric equations here is that now we can see more about, think about these points represent the position of a particle, as I have described, as I have mentioned earlier. You see, any of these values here is to represent the current position of a particle in motion. Then so with our t value changes, and see I keep going steadily for t equals 3 now, and t equals 4, and so on. So these positions that popped out as a plotted point right here, it actually represent as well the direction of our motion. So imagine that now if we have a particle moving on this path, then this setup, this pair of parametric equations we're describing here is not only just to show the plot. It's not only just to show the plot that, hey, here, so we eventually get a line, but the intention behind the scene is it's showing a plot that, hey, on that line right there, on that line if we had a particle, then this pair of parametric equations describe the motion of the particle moving in that direction. So now, as you can see in the animation I have on my computer screen right here, and as I keep adding more t time, as I keep changing t by 1 each time, then I have more points, and so that point, these points together is making up the description of the motion of a particle. So my particle started out here, and then as different t value changes, right? As we change to different t values, then the particle changes to different position, and so it's indicating that we have a particle that moving on the same line right here. But this set of equation, this set of parametric equation describes our motion of the particle moving in this direction, and now we refer to that as the orientation. Okay, and so now on my other board, since I still have a little bit space left, it's another thing to draw out. Okay, so parametric equation. Okay, also, or just a setup of parametric equation. Okay, give or describe. That's the better. Okay. Describe the motion, all right, of a particle on a path. So a path is just a path, but now if we place a particle there, then our pair of parametric equations will describe the motion of that particle on that path right here. And here with the, importantly, orientation. Orientation. Okay. So in in our picture here, in the path that we're having here, it's just a straight line, and our point, our particle is moving in that direction right there. But in other problem, it could be on the exact same line, on the exact same path, but with a different pair of parametric equations, we can describe our particle to move backward. It could be a completely different pair of parametric equation that describe the motion on the exact same path, but going the opposite direction. And so directions and turning directions and all that, we refer to that as orientation. Okay, because now I use this general term here simply because later on sometimes path will go in a looping. Okay, and so that's why it's called orientation, because sometimes it has direction, but then a lot of time later on it will go into as a looping right there. So there's the direction that go clockwise, counterclockwise or clockwise right there, and that's eventually we serve that purpose. So here I'm just saying, it's the particle on a path, right, with orientation, or maybe let me just be precise here. Orientations or direction / direction. How's that? Okay, so if it's just simply an open curve like this, an open path right here, do not close and loop together, then it's just a direction, either we heading that way or we heading this way. Or if it's a looping, then it's an orientation, either we going counterclockwise or clockwise. Okay, and that's the usefulness of using parametric equations like that for that. All right, so now I am going to clear up my board and allow me to start introducing some example. And throughout a couple of these examples, I actually okay, so now I'm about to give a couple of examples, and here's the thing. Back at my time learning about parametric equation, it was such a huge pain because we did not have I back then did not have did not have decimals, and we had very basic calculators. So everything, even back to the table of values that I already erased up here, we had to completely build it manually, meaning everything was by hand with papers and pencils, and then you have to plot everything on the graph. So the process was a lot slower back then at my time right there. But let me now, since at the time when I was preparing this particular lecture over here, I found out maybe in these days any viewers or actually arriving at who actually arrived at this lesson of mine have already been anyone here is in the 21st century and you got all the powerful technology. So why not use the decimals here? So I'm also it's not only just about showing the example, but I also want to show a couple of decimals tricks right here. So I really don't mean to advertise for decimals or anything like that, but when it comes to this point right here, the decimals actually for me serve this purpose a lot better than the standard TI calculator. And so I am going to show the viewers, including my students here, how to use decimals. But to describe, to kind of use decimal to have a clear and solid understanding of your parametric equations. Yeah. Okay, and so let's look at example 1 right here. And example 1 is simply just we are given a set of parametric equations. Let's say about x of t is equal to t squared minus 2, and y of t is t. Okay, and so now the first thing is to draw a table of values. So if you're working with papers and pencil, then it is going to look like something like this. We're going to construct a value of t, and then a column for t, and then this time we are, and that's why it's thankfully that we have decimals now. that we can build the table here as lengthy as we want, so that we can have a good picture, a good description enough of the motion being described, of the motion of the particle that's being that's described by this pair of parametric equations. Okay, and so I will also bring decimals on screen, and so for viewers out there, I recommend that at the same time you watch this on maybe on your little mobile device, but make sure you have a laptop so that you can also work with these exercises at the same time right there. And then of course for my students, you will learn a good amount of experience and have a good hands-on experience here. So the x value is this column, and the y value is this column here. Okay, so. And really, you can start out with any t value here. Let's say we want to start out with t equals, let me double check with -4. Okay, so let's look at t equals -4. And so, and of course, the values here will come out accordingly, but I am going to, whoever decide to go with the paper version, papers and pencil, feel free to follow along with my table and write it on your tables on paper. But you see, I just want to show you that this exact work right here can be done completely on decimals, and it saves you a lot of time, and we can actually expand our capabilities to see the entire graphs. Because back at my time, I was only to, if we use this with paper, then there's no way to build a lengthy table, and so we won't be able to see much of these. And it took years to have a nice full understanding of that. But now, since we have better technologies, why not using that so that you can learn faster and have more understanding faster? So on my computer screen here, give me 1 second to prepare the value. Okay, so this is what I want to show users right here. Okay, so now let's switch over to my. All right, so here's my full view of the decimal screen right here. So now when we on this command line, if you want to insert a table of values similar to what I have done earlier in the very beginning introduction, and which is right here, this is how we can do it. I am going to, on decimals, and of course decimals.com and then /calculator. Or to access this page right here, you can simply, on a new tab right here, you can just simply click decimals right there. Okay, and there's the graphing calculator. Click on that, and it will bring you into your standard decimals. And then this button right here gives you some more settings of your graphing space. But since I already had my prepared one right here, so any of these can be a minor adjustment that you can adjust on your own right there. But so now, what you want to do here is to click on the Add button right here, and now we want to add a table right here on decimal. Okay, but now by default, decimal treat this table as a 2 columns table, where just the standard x column and the y column being the dependence variable. We want to clear this out, so click on that to clear that out. We want to change this variable here. Instead of calling that x1, I want to change that to the t variable. Okay, and now in this column here, just go ahead and highlight the whole variable's name right there. And now I am going to type in the name of our function for x. So I'm going to use this column for x, and I'm going to create another column here for y. So my x here, this column, I'm going to rename it. But actually, we don't even have to rename anything. We're just going to type in the actual parametric equation for x right here. So t squared minus 2. All right, so right here, t squared, right, minus 2. Okay, and I don't need to, so make sure you see, because if we click on that, and eventually when we have a value for t, it's going to pop out some unnecessary plot right here. We don't need that, so click on that to clear out that. Here in my next column right here, I am going to type now decimal. In the end, any technology, I believe, has a weakness. So decimal still has a weakness that if you simply type t, it will confuse with this column t. Okay, so just type 1t, it will understand. And so that, like I said, because any technology is limited, but this means this is our y value. This is our y value. Our y value is determined by the formula y of t equals t. But like I said, decimal, when you just simply type t, then it's going to misunderstand as your t column that was in the very far left here. So we don't want to do that. So we just want to indicate that this is the column as a dependent value, and this is just the independent column here. Okay, and once again, click on that to clear out the graphing feature of that. So now I am going to start out with -4, just like how I put in my table. So decimal now is strong enough to do a quick calculation there for me. So now these are the two corresponding x and y value. This is x value for my position, and my position so my y value is at -4. So my first position when I start out choosing x equals -4 is at 14, -4. That's what it is. And so now this is the next thing I want to do. So now we want to plot this pair. See, our graphing space is permanently reserved for only the x coordinates on the horizontal axis and the y coordinates on the vertical axis. There will never be an axis for t, and that's the whole point. We just want t to be some hidden variable that behind the scenes drives the values of x and y. Okay, and so for now, with only one value for t, we already have a pair of value. I am going to take a pause on that table. I'm now going to click outside of that command entry box right here to the box number 2. I'm going to give a click right there. This is what I'm going to be doing. I'm going to type a open parentheses x1. Okay, just type x1, and then it's going to automatically put the 1 as a subscript with a comma, y1. Okay, close the comma right here, and then hit enter, and then it's going to pop out these two fancy slider feature right here. This is what you want to do. Click on the x1 right here, and you do need to type in the formula for your x value. So it's t square. So square key is the hat key right there, the hat key with a 2. Okay, so t square minus 2. So I'm repeating the formula of our t column, okay, for x1. Okay, and then don't worry about whatever being changed here. And now I am going for once again, I navigate down to the line that says, the command line that says y1 equals 1 right here. Now I want to change that to 1 times t, which is t. That's good enough. Okay, and so now, do you now notice that there's a point right here that's being, if I popped out the actual value, it's 14, -4. That's how I told Desmos to plot our first point as a parametric point right here on the plane. So this is our first point because we start out first we chose t equals -4 to be our start. Okay, and then this is our first starting point. Now if I don't like this color, this purple color, so I am going to go back to my command line right here, click and hold. Okay, and it will pop out a quick little menu right here. I'm going to change that to a black color. It just might, I believe it makes it's best to view with the black color. That's all. Okay, and so now, once we've had the first point successfully constructed, okay, now we're going to go back to this table. It's just simply when the mouse button, the mouse cursor changed to something like this, ready for another typing entry. So click right there, and now I'm going to hit enter to move on to the next row of my table of values. So that means now I'm ready to enter in my next value of t. and with my next value of t, I am going to corresponding receive my next pair of x and y. So trust me, because this is the first time I'm introducing this to my students, okay? Because I'm trying to replace this with the paper and pencils work. So instead of doing this manually on the board, we can now copy and paste this kind of work and make it a lot more interactive on the computer. And once you're on the computer, you will be surprised how much faster it can make for you. Okay? And so again, I'm going to switch back to my screen right here. Okay? Back to that command. How about I'll pick my next x value as being a negative 3.5 right here. I typed it wrong. 3.5. So see how quickly the table has already calculated. Desmos has a really beautiful calculating feature over here. So Desmos has already calculated, so it saved us all that energy. Okay? And then immediately, now if you observed in the graphing area over here, our second point has popped out. There you go. So now we start seeing some change. We change from t equals negative 4 to t equals negative 3.5. We have a position change from 14, negative 4 to 10.25, negative 3.5. Okay, so think about, we now have a particle. So here's our particle, and this is its starting position, and in its next position is here at the next instant of t. So now I'm going to go to my table, and here's the nice thing about Desmos that I really enjoy. Desmos is sensitive and is smart enough. That's how I call it. Desmos is smart enough to recognize the difference between negative 4 and negative 3.5 as a jump. So the jump here, Desmos will recognize as a 0.5 jump. So if I just simply hit enter, Desmos will automatically create the next value being the same jump, 0.5. So that means from negative 3.5 I had previously, then just hit enter, and Desmos will automatically generate the next value for t in a jump of 0.5. So that's why we landed at negative 3. So now when t equals 3, we got our third position. So first, second in the graphing area, third position. Okay, so things are still looking like a line, isn't it? Because, well, we already had our x and y value here. See? So now I'm going to pick the next one. I'm going to just simply hit enter. I'm simply going to hit enter. Now it's going to jump to negative 2.5. And so you can start sensing that it's not linear anymore in this path, these points right here. And see, the first jump, same amount of time, just about a point, same amount of change in t. See, any jump between any two consecutive values of t here is only a 0.5, but look at how much jumps in the actual distance between the point. It was a big jump here and then a shorter jump here, and I'm talking about the shortest physical space between the 2 points here, and it's shorter here. Okay, and so now back on my table, I'm going to hit another enter. Then Desmos will automatically put in my next point right here, being a negative 2. So Desmos is very smart in that way, and then it already calculated all of my x and y values correspondingly. So now I'm starting to recognize more points. But see, the reason I share this with my viewers is that back at my time, it's easy to give up. For students who studied together with me at my time, it was very easy for my classmate to give up because there are too many points. In a graphing problem like this, there are too many points to graph. And so, doing that with papers and pencil, it will take a lot of efforts to eventually see a complete picture. Because right now, we are nowhere near to seeing the complete picture. So unless we have to go further, but going further with the traditional method, papers and pencil, will be very limited to paper size and all that, how much space you have left. And that's why now I share this with my students and all public viewers out there. So now we're going to need a next point. Okay, and so now I'm going to start going a little crazy here. I'm going to keep going. Now you will see all the points here are changing, okay, and creating a path. So now my position of my particle is moving, and as we have enough points, we start seeing a bent away direction. So now that's what I'm talking about. A pair of parametric equations describes the motion. Think about, we have a particle. First it started here, and as my t value goes on, then it changed to a different position. At first it was hard to recognize the shape of the path, but now as we keep adding more, thanks to Desmos, okay, we now can easily recognize that we have our particle is moving it is making motion in a way that it's going pretty much like a parabolic shape right here. It's now easy to recognize we're going in a parabolic path, in a parabolic shape path. Okay, and so now I'm going to keep going. I just want to make sure that we have a as complete as possible. So it keep doing that parabolic shape like that. All right, and so now we are clear that we have a path that goes this way right here. Okay, it's a nice parabolic shape. Okay, and so that's how we can construct now. So why am I showing my students this and my my viewers this? So public viewers, it's just for you to learn, but specifically for students who are learning with me, believe me, there will be, when it gets into this kind of problem about parametric equations somewhere here and there, you will run into the kind of problem where they give you a graph and 5 choices, or maybe 3 choices. 5 is a little too much, okay? Maybe 3 choices of parametric of pairs of parametric equations, and you got to predict which pair is the one that gives you the graph. Say the kind of problem will be they give you a graph. They give you a graph, like say a graph looking like this, and there's 3 pairs x of t, y of t. That's one pair. And then there's another pair x of t, y of t, okay? And then there's another pair x of t, y of t, okay? 3 pairs, like 3 pairs of parametric equation, and they name that A, B, and C right here. And which one here is the match for that graph being given here parametrically? And that's the kind of problem. And so now back at my time doing the kind of problem like this was really a huge pain and such a huge challenge back then, because we did not have a powerful computer back at that time. So we have to do a lot of papers and calculation just to successfully get a good complete, a good portion enough of the graph to come up with, to make a decision. But now, for when I pass this down to the later generations here, for specifically for students who study with me, then you got Desmo. Thanks to Desmo, that you have all these tools right here, then you can quickly, no matter if they give you 3 pairs of parametric equation or 5 pairs, you can hop onto Desmo and quickly draw a graph as how I was showing you that, and then you can easily see the shape and find the best shape that matches your given graph. Okay, and so that's what it is in my intention for this example. So back in the end, what is the whole purpose of this example 1 right here? So example 1 is just, and there will be a couple later examples will be just like this. I just simply give you a pair of parametric equations. You can take your option to go with completely on paper, but we just first we start out building a table of values. Okay, we build a table of values, and then after we build a table of values, we want to observe. We're gonna put these points. We're gonna plot these points, these pair of values on the graphing plane, so that we can observe the trace. We can observe the path that was created by all these points together. Okay, so you start out with a pair of parametric equation. We're gonna build a table of values, and we're gonna put it on the plane right there, on the graphing plane, to observe what kind of path our points create right here, or what kind of path our point stay on. That's all it is in this example and in the next few examples. And another thing that I already mentioned, I just want to show these so that you students of mine or viewers out there, you're not only learning about, you not only strengthen your understanding of parametric equation, but you also learn how you can effectively use technology to enforce your understanding and effectively use that to solve quite a few problems. And like I share with anyone here, the major kind of problem that has always been a challenge back at my time at least was the kind of problem when we find the right match. And of course, in these days, the reason I show this Desmo trick again is another reason I show this Desmo trick is that you can see that how you build your scatter point from scratch. If you just simply use a TI 83 and 84 calculator, it has a really nice feature, but it just boom, here you go, here's the graph. But you learn nothing. You don't learn about the direction of where these points are going. Okay, because see, same path, but it could be a different pairs, the same path here, but it could be a bit different pairs of a parametric equation that gives you the path that goes like this. Okay, go in one direction, or the same path here, but it could be a different pairs of parametric equation that going the opposite direction right there. And so doing it this route right here with decimals, yes, it does take a little bit of time right there, but it gives you a full understanding of how these of how changes in t values cause your point to jump location, to jump position, to eventually form into an oriented path like that. Okay, but if you just simply use a TI-83 calculator and type it in and boom, get your graph, then you only what you see is simply just a graph, just a a crazy looking curve right in front of you, but you will learn nothing about how your particle is moving on that. Okay, all right. So now we're good with this example. So let me now head out to example 2. All right, so in example 2, let's now look at and pretty much the same kind of problem. I am going to be giving out, we are given a pair of parametric equations. How about x of t equals, all right, so cosine of t, and y of t here to equals sine of t. Okay, so just like that. So before I switch over to decimals, then for students who still want to stay with writing your work on papers and pencil, you still can. We create a table of values. One column here for t, one column for x of t, and one column will be for y of t. But if you decide to go this route using papers and pencil, then you got to prepare with a lot of paper space right here, and it's going to be quite time consuming for you. Okay, and so now, so another thing I hope you already caught up to this point is make sure you put your, even though independent values, but put your t values in organized order. Okay, so we got to order all of our t values from, you can go from the highest to lowest, or you can go from lowest to highest. I tend to go from lowest because it's starting out. That's the way how it is. We start out with lowest value and we go on to higher value down the table right here. Okay, and so now these two are parametric equations that involve trig function. Whatever that is, but it will work. We traditionally, when it comes to trig function, then it's easier that we go with the radians, the units in pi right here. So I can start out with t equals 0. Okay, then our next value here can be think about the smallest common angle that we can have on when we are studying trigonometry. The smallest common angle is a pi over 6. Okay, and then we come to a pi over 4 and a pi over 3, and so on and so on. Okay, and so and these are of course in the increasing order from low to high right here. All right, so now I am again going to prepare my calculator screen right here. All right, and I invite viewers to work along with me as well. So back on my calculator screen here, now I am going to change this to cosine of t, and this column here to sine of t. And so I also have to make sure you also need to make sure you change these expression as well. So this is x1 here is cosine of t, and that line here is changed to sine of t. Okay, and then these three lines right here are responsible for making the plots of the points. But now this is our main brain right here, our table of values here. So I'm starting out with 0. But now since we're using the values that are in pi units, so the decimals is not that sensitive with pi units yet. So here we just enter manually. So pi type of pi, that's pi lowercase pi, that's pi divided by 6, so pi over 6. So now we got our next point right here. So our first point started out here. If I hope anyone viewing the video already noticed. So right when we type in t equals 0, that's this point. Let me quickly delete this out. See, that was the point where we had t equals 0. So cosine of t equals 1, cosine of 0 equals 1, and sine of 0 equals 0. Just like how we study trigonometry. And now when t equals pi over 6, pi slash 6, pi over 6. And now we got these two values. And of course, decimal is not showing the output here for our trig function in roots and all that. But these are exact values of this is cosine of pi over 6 right here, which is a square root 3 over 2, and this is a 1/2 like that. Okay, and you see when we hit enter this time, decimal won't be able to automatically recognize the jump between 0 and pi over 6 because we're running in pi units right here. But we can always type it in manually, and it doesn't take too much time. So pi over 4, that's the next angle. So now you can see that a third value jumped out right here. So it's already in somehow a bent shape already. So this is how, if our position is here, if our particle was here at the start, then the second position is here. The third position is here. Okay, second position, third position. And now let's look at the fourth position. Let's say I'm going to type in pi over 3 right here. So now it's popped out the next value here being, so it seems like we're going in a round shape right here, in a round shape. Okay, I'm kind of revealing that truth, but that's still not clear, right? But thanks to decimal now, thanks to decimals, we see back at my time, I had to do a lot of these just to eventually trace and guess, and there are a lot of unsure to happen back then when it was my time. But now with decimal, we can tear it all down and make everything come out to light. Okay, so pi over 3 is our fourth position. So our next position, we can just call that how about the pi over 2. Okay, and so now our position is right here. Okay, so t is of course not shown within the picture here, but t is behind the scenes that's responsible for changing position of these 2 points. And so now as we keep observing how these points changing position, how our particle jump from one spot to another spot right here, then we start sensing some kind of path being behind the scenes here. So the next one here is how about a 2 pi over 3. Okay, so we jump, so it looks like it's becoming more obvious and more obvious that we're going in a round circle already. It's already that clear. But now don't rush. We can quickly jump to a 3 pi over 4. Okay, and then our next position is here, and then so we can easily go through all of our common values on a unit circle right there, and we can see this. All right, and so now my next one here, I'm gonna go with how about 5 pi over 6. Okay, and it gave me that point right there is our latest position, and then our next position here is at pi. How's that? Okay, so now it's becoming more clear that we're traveling our point, and see, it already gave a perfect description of our direction, of our orientation on this loop right here, on this round path right here, because we're going in this counterclockwise direction. All right, so I'm gonna still keep growing my table further. So how about the next one after pi would be, how about 7 pi over 6. Okay, and I have that point, and then I'll have this 5 pi over 4. Okay, and then I'm going to move on to my next point being four pi over 3. All right, and my next point here would be 3 pi over 4. All right. I mean over 2. All right. And then my next point here, I can move to, okay, and so on and so on. Five pi over 3. All right, and then 7 pi over 4, and then the next one here is going to be 11 pi over 6. All right, and the last one here is at 2 pi. But see, when we're at 2 pi, this point here, when t equals 2 pi, of course, in terms of the t value, 2 pi is different with 0, but then our actual position here lands right into our starting point. That means this kind of path here is what I use, is the term that I used earlier. It's a closed loop. Okay, it's a closed path because start points and ending points meet together at one spot right here. Okay, and so you see start point was at 0, 0, I mean 1, 0 when t was equal to 0. And when t changed to 2 pi, right, we went the whole round and we landed right at that same point where we started it, and that's why I use that term. It's a closed loop. The path itself here is a closed loop, and so in this way right here, the direction now is being referred as the orientation, just like how I used that in red term earlier. Okay, and now without putting the actual putting up the actual circle, then you can also see. I mean, without putting up the actual graph, then you already see that this needless to argue. It's a circle. Okay, the path here is a circle, and we just now observed table of values, and then we made plots, right? And we now saw our complete path right here. Okay, and of course, this table of values can keep growing further, but as we keep growing further, then we're gonna just make more loops around this path right here. Okay, so there's no point of doing that. All right, and so that's how we have done our example 2 right here as an experience right there. And then so you can see that, and you can see how this parametric equation here, and this set of parametric equations give you a graph right there. Okay, give you a path, and that path also has a description of how a particle on that graph is moving along the graph. Okay, all right, and so now I hope you can take that skill and get ready for I hope what I show here with the decimal screen is universal enough so that you can use at any time, really any time, so that you can get through with a lot of your assignments here, especially the kind of problem where I raised your awareness earlier about they give you a graph and you're gonna have about 2 to 3 or maybe 5 sometimes, right? 2 to 3 or maybe 5 pairs of parametric equation, and which one of those pairs of parametric equations gives the graph as given here, and you can now have decimals to get your work done. Okay, so now let's head out to another example, and this example here, for this example, we don't need decimals, but we're gonna stay on traditional papers and pencil methods right here because we're doing some algebra. Okay, and this is the reason why, as I'm saying, this current first half of our lecture on parametric equation, then we don't need any calculus understanding. So just like how I said earlier, this can be used for a student in pre-calculus to learn as well, because some instructor of pre-calculus course decide to teach a parametric equation at that early stage in learning math. Okay, so let me now call this example 3. So now before we move on into example 3 here, then I got to clarify the equations we've had so far always exist as a set, and for now any of our set is a pair, 2 equations. There's one for x, there's one for y, but it will never come as only one single one. Okay, so at least it has to be 2, because for now at least we learn our graphing system got any of our points got 2 values, x and y. Okay, and so now I'm looking, this is the instruction of our example right here. Let's find the Cartesian. Okay, let's find the Cartesian equation from the given set of parametric equations. Okay, so now I'm going to write down part A, and I will explain what it means by find the Cartesian equation from the given set. So we have to know what our given set is first. So our given set of equation here is, how about x of t here is 5 minus 4t, and y of t is 2 plus 4t. And to be honest with anyone viewing my video, this is indeed the pair of parametric equation that I started out introducing the idea of parametric equations. But that's just we have already seen the plotting of that and how it came into a line. Okay, how the points being plotted out from this pair of equations formed into a path, and that path was a line. That's to be precise right there. Okay, and so now we're not plotting again because you have already seen the plot of this parametric equation. So this is what I want to do. What does that mean by Cartesian equation? You see, let me bring up a couple of examples and you will immediately understand. Cartesian equation is something like this. Y equals 4x plus 3. This equation of mine only involves x variable as the value on the horizontal coordinates, and the y variable as the value on the vertical coordinates, like that. Or x squared plus y squared equals 10, something like that. Any of these that only involve two variables, x and y. And x and y are associated with the graphing systems in a sense that x is the value on the horizontal axis and y is the value on the vertical axis. Then any of these being regarded as the Cartesian equation, because the graphing system we have been using since long ago is famously known as the Cartesian graphing system, right there, the Cartesian graphing system. Okay, so now how do we do that? How do we bring our pair of parametric equations into the Cartesian equation? Okay, and so there has never been a hard how-to instruction of how to do this. And I have to give a friendly warning ahead of time. We need to definitely use a lot of algebra. Okay, and that's why, like I said, this lesson here, the first half of that, which is currently where we're at, right there, can also be useful for students in pre-calculus who also happen to learn about parametric equation. So now in the end, yes, I see x of t as a function x and being expressed as 5 minus 4t. It's a function dependent on t. And y here is as function y of t, formally as a function dependent on t, 2 plus t. Okay, but now in the end, think about if we can just skip the t notation here. It's just the real truth. It's just x as a variable. A function is a variable. So x is a variable 5 minus 4t equals 5 minus 4t, and at the same time y equals 2 plus t. Okay, and so the easiest reach I can go from here, from this x, basically we have two separate equations here for now. Okay, so from this left-hand side equation, x equals 5 minus 4t, you can do this. I'm going to subtract 5 from both sides to yield to give x minus 5 equals negative 40. And that means I can further divide both sides by negative 4 to bring myself to x minus 5 over negative 4 equals t. Okay. Or we can rewrite this as another way of rewriting this. We can rewrite this left-hand side here as 5 minus x over 4. Okay, to get rid of the negative sign in the denominator, which is a lot of time a little bit awkward. Okay, but either you can write x minus 5 all over negative 4 equals t, or 5 minus x over 4, no negative, equals t. Either way. Okay, but that's pretty dead end. That's pretty much dead end for our equation here on the left. So what about on the right hand side? Y equals 2 plus t. Then I can also subtract 2 from both sides and gives t. So this is one similarity that happens between the two works I've done here. I solve for t in terms of the other variable in both of my equations here. Okay, but I'm not saying this is the only way all the time. I'm not saying this is the only way all the time, but at least this is the method that makes sense the most. We solve for t from this x equation, and we also solve for t from this y equation. What's good about that? What's good about that? Now t equals x minus 5 over negative 4, or 5 minus x over 4, depending on how you want to see it. And at the same time, t equals y minus 2. So doesn't it now make sense that if t, one variable but equals to two different expressions, then isn't that obvious? Well, anyone viewing this video now is mature enough to see if one same variable equals to two different expressions, then that means consequently y minus 2 as one expression will be equal to the other expression, x minus 5 over negative 4. Congratulations. This is your first problem where you turn a pair of parametric equations into this is what we call the Cartesian equation right here. It now only involves two variables, x and y, where x here represents the value on the horizontal axis, and y here is the value on the vertical axis. And what's good about a Cartesian equation? It's the equation that points out the relationship between the horizontal and the vertical value right there. The horizontal and the vertical value, and that's what it's called, Cartesian equation. And then if you're not happy with this form, if you are not satisfied with this form, then so from that point, you have your choice. So right now, let me rewrite it down. Y minus 2, x minus 5 over negative 4. And I'm pretty sure, trust me, right now what I've shown earlier is a just fine looking Cartesian equation, but you will want to definitely do this. So I am going to multiply the negative 4 to both sides of my current equation, even though I already had my first version of the Cartesian equation for this current pair of parametric equations. But I still want to go a little further. So, and it's all the algebra. See, all the solving steps were algebra. And now it's rearranging this equation. Negative 4 multiplied to both sides. So negative 4 times y minus 2 equals x minus 5. Okay, nothing yet. I'm going to distribute the negative 4 to each term here inside of my parentheses. So here we're looking at minus 4y plus 8 equals x minus 5. And I mean minus. Okay, but I wrote plus. And now I am going to bring all the variable terms on one side. So, and how about this term here was already positive, so I'm going to bring that to the other side. And I'm going to bring the non-variable term, which is the negative 5 here, to the opposite side. So now we're looking at 13 equals x plus 4y. Does anybody here viewing this video recognize this equation? Ladies and gentlemen, this equation is simply, yes, as a type of equation. We call that it's Cartesian equation, just like that earlier, but now being a little more specific. Hey, wait a minute, this is just a linear equation. The equation of a line. This is a linear equation. Okay, this is a linear equation. No wonder why. Now let me pop back that our decimal screen right here. Okay, give me a minute to prepare that. All right, here we go. So back to the sketch that we've had earlier. These are the plotting points. Okay, so I started out, if I remember correctly, we started out at -2 for t, and then we went down to -1, okay, and we continue going on. I don't think this was the correct one that we used. Here, this was 2 plus. Okay, 2 plus. All right, and then let me put my zoom further out. And there are my points right there. So we've made 3 values for t so far. And so now if we keep going, okay, and then these points, as we have already seen, they form into a line. They were forming into a line. And so now let me actually put in, okay, so on our board here, now I am going to graph this line together with what we've had on the decimal screens there. So I'm going to graph x plus 4y, and I hope you all understand this is the same as x plus 4y equals 13. I am going to graph this linear equation on the same graphing space on the decimal screen right there. So here we go. So now I'm going to open a new command line, and I just simply type in x plus 4y, okay, equals 13. Look at what it does here. So that now even proves further and certifies, verifies further that all of these points here are on this path, and this path is a line that's as an equation. So this is the Cartesian equation of that line, is x plus 4y equals 13. Okay, and so now at this point, of course, we're still not done with the, and let me change this color to red right there. Okay, but now at this point, even though we're not done with example 3 here, but now I have to point out right here, you see, again, let me come back to the question about why is it useful to use parametric equation. Because if we only show, now let me hide away all these points right here. If we only showed about, if we only use decimal to type in this equation, then yes, we got a line, just like what we want. But now that's just simply a line. On this line, we will have no idea about, if we place a particle here, where will it move? In which direction will it make motion? But now, having describing our particle as a pair of parametric equations, then see, we're starting out with some chosen time, and we go to the next time value. So our starting time here is -2 for t. Our starting t value is -2, and so consequently we ended up with 13 for x, 0 for y. So our first point is here, and then in our next point we can choose a -1. So as our parameter t changed from -2 to -1, we jump position from this position 13, 0 to 9, 1. And then now we continue our journey. So now we're going to start recognizing, putting more points in. We feel we have a good, clear understanding of where our particle is moving on this, along this path here. It's a path, but this pair of parametric equations describe the motion of our particle on this path here, in that direction. And later on, as I will go on even further, then you will, when you get into your calculus understanding, then it will have even the same path right here, but points can be moving even faster or slower. Okay, but so that's the usefulness of using parametric equations right there. Okay, and so we can keep going a few more values right there, and you can see more points. And so just the Cartesian equation right here is simply giving you a line, but now together with your parametric equations, you have a clear understanding that this path here is being created by the going in this direction. Okay. And so now, let's get ready for part B of our example. So in our part B, same purpose right here. So a good experience we drew out from this part A of our example here is that a lot of time it's good to solve for t. So what I did earlier was I solved for t for the x equation, and I also solved for t for the y equation. And then from there on, I equate two equations together. That's the most common one. But now let me tell you, when it gets to this, you must also rely on your own the creativity in algebra work like that, because solving for t is not always will not always work. Okay, I admit most of the time it works like that, but it won't always work. There are some equations that some pair of parametric equation that requires more creativity than that. So you gotta strengthen your algebra so that you become more sharpened with these skills right here. But let's look at B right here, and you will understand exactly what I mean. So now, how about x of t equals 2 minus t squared? Okay, and I have so in my pair here, and at the same time y of t equals t cubed minus 4. Okay, and so yes, just like the earlier work, I am going to go ahead and write this equation simply as x to keep things less confusing. So x as a variable itself equals 2 minus t squared. Okay, and then here I am going to solve for t. Well, just if we learned that from the past experience, why not using it again? Okay, so just like that, I'm going to look at x minus 2 equals negative t squared. Okay, and then and as I said, we look for a way to solve for t in terms of x now. And so I can cancel both, I can divide both sides by the negative sign. So t squared equals to, how about 2 minus x? Okay, but here's the thing. Let me advise. How about let's take a quick pause here. Okay, let's take a quick pause here, because I don't want to solve for t right from here yet, because solving for t here is a little dangerous. We will run into a plus and minus square root expression and all that crazy thing. Okay, so let's turn our focus to the other equation. Similarly, I'm trying my best to solve for t. So y equals t cubed minus 4. I'm going to rewrite it as y equal t cubed minus 4. And then now I'm going to solve for t by adding 4 to the other side. So here y plus 4 equals t cubed. And I feel hesitating again that, hey, I don't want to take cube root, because cube root is, I mean, any kind of root is, when it's actually come to root, believe me, anyone is going to be as hesitating to deal with root as I do right here, as I am right here. So because it's dangerous, especially when you're taking even root, you're going to run into a plus and minus, and this root here, there's still a lot of unpredicted things happening waiting for us. And so, but here's how we can do a quick little trick here. So instead of directly solve for t, we still solve for t, but this is what I'm doing. Why don't we square both sides? Instead of taking roots both sides, or taking square roots both sides, or taking cube roots both sides, why don't we square both sides? You see what I mean when we get to that destination. Y plus 4 square, but the right hand side now becomes a t to the 6th power. Hey, because t cubed square is a t to the 6th power. Okay, that's one thing. So y plus 4 all square equals t to the 6th. And so now, on this equation, I squared both sides. On that equation, why don't we take the cube of both sides? So now I'm going to end up with 2 minus x cubed equals t to the 6th. Okay. I did not solve for t directly, but I actually solved. Look at what I did right here. Look at what we have led ourselves to. I did not solve for t, but I actually solved for t to the 6th. So I now know that t to the 6th equals that, and at the same time t to the 6th equals this. Okay, and so now, what's good about that? All right, so on my next board, and just again give me another minute or so to erase the board. And so now we have on one hand 2 minus x cubed equals t to the 6. And on the other hand, we have, for the other equation, we got y plus 4 square equals t to the 6. Now, just like part A, t to the 6 simultaneously at the same time equal to these two expressions. No t in there. So now we can go ahead and equate these things. That's how math works. So 2 minus x cubed equals y plus 4 square. Ladies and gentlemen, this is another Cartesian equation of yours right here. And if you type this into decimal, it will give you a graph. I'm not saying that it's a function. I'm just saying it's an equation that's relating the horizontal x value and the vertical y value. Okay? And so again, let me quickly pop in with a few values. Let me prepare my decimal screen right here. So I just want to do that quick demonstration right there. All right, on our decimal screen, I have already quickly spent a little time to change this. Change our set of parametric equations here. And so our table of values is now ready for action. So how about I am going to just first, we are going to plot our points that came out from the parametric equations. So I'm going to start out with t equals -2. And I have a value -2 and -12. Oops, where's the point? So here's the thing. Sometimes the actual point may be out of the viewing window here. So you on your mouse like that, and that's why I'm not very sure how this decimal is run on a mobile device, but I highly recommend running this decimal's device, decimal's program here on a computer, on an actual computer. So with an actual computer, then you can just use your mouse, the scrolling wheel of your mouse, and scroll it down right here, and it's gonna zoom out further. So now with your graph zoomed out further enough, then you will start seeing your point. So your first point is here at coordinates -2, -12. Okay, and so now I'm gonna throw in the next value, but let me try to make, so because we have such a powerful decimal, so why not going with a jump of only about 0.5, so -1.5 here. Okay, and so now we already start seeing the next point. And so now decimal will remember our jump here. So we just simply hit enter, and the next one here will automatically be at the same jump of t value, 0.5. So there's my next point. And then I'm going to keep going. There you go. And so we already start seeing some bending shape right there. Okay, so it looks like it did some kind of bend, but going into a corner right here and heading out right there. Okay, and we keep doing that. All right, so now after seeing, it looks almost like a V shape, but because in the end our points are discrete. Now really we can actually go back to all the way from beginning, and we can do this as well. My second point, I can go with -1.75, which is only a jump of 0.25 like that. Then decimal will restore the jump to be smaller. And so the smaller of the jump, we're going to see the better refinement of our graph like that. Okay, so now it reveals the curving shape a little better. Okay. And now we can zoom it in a little bit decently right there. All right, and so now with all the values here being displayed, and of course, see with the power, with decimals being so powerful, then we don't have to do any of these on papers and pencil anymore. And so we got the points plotted, and we already sense the direction. So it went this way. This is start, and we going to here, and then we keep heading that way. Okay, so now here's the graph. This was the Cartesian equation for the earlier problem. But now if we're going 2 minus x being cubed, okay, and so hat 3, that's for raised to the power 3, to the third power, and then in parentheses y plus 4, okay, raised to the square power. All right, ladies and gentlemen, are you ready to see the actual graph? There you are. So now you click the graph feature, turn on the graph, it's here. So this graph perfectly contains all your points. So now we have a clear, the path is here in red color, okay, and your points were moving in this direction. It's moving in this direction right here. It's moving that way as my mouse cursor is going, and then heading the other way. Okay, So there's one more example where we can find the Cartesian the equation of our pair of parametric equations. Okay, so but I really want to give as much examples as I can so that you can learn more experience. And I have another advice at this point when it comes to being able to write a set of parametric equation into a Cartesian equation outside of my own lessons right here. Learn that from other professors, learn from other YouTube video lessons to see how you can write from parametric equation into a Cartesian, and you will build your own foundation of how you can do these. But it's strictly based. This work is strictly based on the algebra. So your solid background in algebra will be the biggest key right there for that. Okay, so now let's look at part C of our example. All right, so part C here, I am looking at how about x of t equals 5 cosine of t. Okay, and we got y of t equals 5 sine of t. Okay, we have already seen that. And so now here's how it works out. And surprisingly, this problem where x and y are both being defined in terms of some sine or cosine, then this is a pretty standard trick right here. And I hope I share this lesson here. After this lesson, you will learn some experience. But you see, x equals 5 cosine of t. So why don't we, instead of rushing into solving for t, so we're going to have to deal with inverse, all that crazy inverse of cosine of x. We don't want to do that. Try to stay as simple as we can. So here, why don't we just, it's all about experimenting things out. Try to get some experience. So x squared, out of nowhere, I mean, so that's why here I'm already experienced. I'm handing it down to you. You can take this as another trick, okay? Equals 25 times cosine squared of t. And I'm kind of dead end right there. Okay, let's hold on to that. And now this is the same as y equals 5 sine of t. Okay, and so I'm doing the similar trick with that. How about squaring both sides of this? It gives me y squared equals 25 sine squared of t. Okay, and it didn't tell us much. It's still in the end two separate things and nothing related. But here's the thing. Why don't we? And it's all about why don't we. So I'm trying to lead your attention into different directions like that. So why don't we just simply add these two equations side by side? So x squared plus y squared, will equal to 25 cosine squared. Okay, 25 cosine squared of t plus 25 sine squared of t. Do you agree with me on that? Okay, and of course it seems ridiculous that I'm asking the online public viewers on this, but what I mean is when it gets to this point, I want to trigger some of your memory about some famous trigonometry identity right here. Okay, we have a common factor of 25, and now there's, so on my next board here, all right, so the x squared plus y squared is equal to 25 cosine squared of t plus 25 sine squared of t. But on the right hand side, we can factor out the 25. And now we're looking at cosine squared of t plus sine squared of t. Okay, and x squared plus y squared is here. Okay, and so the cosine squared plus sine squared is, in other words, it's just 1. It's just our famous Pythagorean identity for trigonometry. In trigonometry, And so all that here now reduced down to x squared plus y squared equals 25 times 1, which is 25. But wait a minute, isn't this a Cartesian equation? It is. It is a Cartesian equation. X squared plus y squared equals 25. Okay? And as a matter of fact, for any of you who have already gone through some pre-calculus course right here, okay, and even I said in the beginning, this lecture I'm delivering here can also be used for the pre-calculus to learn, but anyone learning this material here, parametric equation, should have also seen this already in courses before that. So the equation x squared plus y squared equals 25 is the famous equation for a circle centering at 0, 0 with radius 5 here. And I will show that on decimals again. All right, so I'll take another minute or so to clear out my table with the all right. All right, so for your best learning, why don't I just show you how I work directly on with this. So now I'm going to go back to each of my column. I'm going to change that to our designated parametric equation. So 5 sine of t here for the y column. This is the x column, this is the y column, and this is the t column. And I'm also going to need to change here to 5 times the cosine of t. And this here is 5 times the sine of t. And I will change that later on. Okay, this was for the very preceding example. But now we have seen this already. But we can start out with t equals 0. And it gives us a point right there. Okay, and here I can actually zoom it in a little bit more. Okay, so our point here is at 5, 0. And now we can move on to the next point here being pi over 6. And now it's pi over 4. And now it's pi over 3. Pi over 2. Okay, and very similar to the one we have had earlier. That's a little too rushing. So 7 pi over 6, okay, 5 pi over 4, 4 pi over 3, 3 pi over 2, and the next one when t equals 5, 5 pi over 3, okay, and 7 pi over 4, and then 11 pi over 6. All right, and the last one is a 2 pi. Okay, so very similar to the one we have had earlier in our example. That was in our example 2 earlier. Then all of our points here create a path that is in a loop. And our beginning point on the table of value here is 5, 0, and our ending point when t equals 2 pi is also a 5, 0. So we complete a loop right here. Okay, but this time the loop here, well, so far with these discrete points, then it looks like a circle. We're not firm yet. Okay, but now at least it seems like it formed into a path, and it closed into the starting point right there, the start point here, and then it went around in the counterclockwise direction, as you have seen through the motion there, and then it popped back into that beginning point. And so now let's type in our equation, our Cartesian equation here. So x squared that we have already arrived to plus y squared and equals 25. Okay, so now let's look at what that is. There you go. And so now it shows what this equation, this Cartesian equation just now shows us here the equation of a circle. So what we have here as a path is a circle, but now it's only shows just the Cartesian equation itself. It only shows a circle. But now with the understanding of our parametric equation, then we are describing a particle on the circle that's moving counterclockwise on the circle. Okay, and so that's the whole idea about parametric equations again, and together with this example 3, what we've learned here is how we can write from and I hope you have learned in somewhere a decent amount of experience for converting from a set of parametric equations into a Cartesian equation. But like I said, it is impossible for me to show every example in a short video like this, in a video like this. And so outside of my lesson here, go ahead and hop onto the internet and search for other problems from other professors and from other instructors, and they will be delivering different experiences, and you will add more to your own experience. Okay, and so that was about example 3 right there. So now let me bring you into example 4, and this kind of example, this kind of problem that I'm about to introduce in example 4 is also famous on its own right here. Okay, so all right, so in example 4, here's the instruction for our example 4 here. Let's say x of t, we are given x of t equals 2 minus t, and y of t equals 3t minus 1. Okay, so we want to give a parameterization okay, we want to give a parameterization that reverses, okay, so here's the term here, that reverses the direction, or if it's a loop, it's an orientation, so it reverses the direction or orientation, okay, of the particle, so on the path. All right, so I am now going to step away on this board and to clear out my board space, and then for viewers who have enough, or you can feel free to pause the video and read and understand a little bit enough. But before I actually explain what that is, I'm going to get my board ready for on the other hand. And now I'm also going to get my Desmo screen ready for this. All right. So now on my other board, this is what's happening, just scratch work. So hopefully you have read enough and have had a long time enough to read and try to understand the instruction of this problem. But so here's, first of all, let's do a little scratch work, okay? So x equals 2 minus t and y equals 3t minus 1. I mean, we can quickly find out what path this is by, you see, the whole reason of walking you through example 3 is that sometimes in your skill, with your skill of being able to write a set of parametric equations into Cartesian equation can quickly determine what kind of path your pair of parametric equations will go into. And then once you actually know what your path is, then we actually do the plotting. We actually do the plotting of the path so that we can see the actual direction or the actual orientation. So you can see that the order of work, when I was actually doing the demonstration, that throughout example 3, I actually got done with the Cartesian equation, and then I took you back to Desmo screen so that you can learn about we can put the graphs on, and then we can see the direction of all the points moving. So here, let's kind of go it that way. So this is easily the same as t equals 2 minus x. Okay, and this can easily be the same as y plus 1 over 3 equals t. And so that we can easily equate 2 minus x with y plus 1 over 3. And we can multiply both sides by 3 here to give us a 6 minus 3x equals y plus 1. And so here it actually now turns out to be a linear equation for us. 3x plus y, subtracting that 1 to the other side, 3x plus y equals 5. 3x plus 5 equals 5. But it's now a linear equation. That means the graph that Desmos will give is going to be a line. Okay? And I'm still not getting into any explanation about what that is. Let's quickly get into Desmos right here. Okay, so on Desmos, here's what's happening. So I'm going to modify this problem right here. That was 3x plus y equals 5. Okay, and now we have a line. Okay, so there's our line. So now I know that once I actually plot, and I have already, the reason I took a little time earlier so that I can prepare the screen. But when we see, this is our parametric equation right here, our set of parametric equations. So now when we actually plot it, we want to observe that, hey, because as I have explained earlier, that a path is just a path. Okay? It's just a physical picture of the path. But what matters now and what's useful about a pair of parametric equations is that it will give a description of if we had a particle on that path, then where would that particle go? In which direction? So the path now we have is clearly a line. The path now we have is clearly a line. So think about there's a particle here at start, t equals 0. Where will the particle go? Which direction will the particle go on this path? That's the question. Okay? But it's still, I still didn't get to the actual explanation. I still didn't get to the actual explanation of what this is, what this example is all about. But now I'm going to go with 1. Actually, that's such a huge jump. So how about 0.5? Okay, then the next one is a 1. Okay, then 0.5. So now, all right, so now we can see that on this path, then our particle is moving backward on the line. It's moving this way as my mouse is pointing. And as that's how the points were animating, were describing. Okay, so now getting back on our problem. What is a parametrization? A parametrization is just a way to parametrically express your path. Okay, so this is already a parametrization. This pair of equations here is already a parametrization. But just now, just like how you saw on screen, with this current parametrization right here, then out on that same path. On that same path, we had our point was going in that way, as you already saw. So again, on that path, our particle was moving this way up. Okay, but then in the end, what we have here is already a parametrization. So here's how to understand about this problem. This problem wants you to write a different, give a different parametric expression. That's what it means by give a parametrization, a different expression, a different parametric expression of this pair, so that on the same path, but we're gonna go in the opposite direction, and that's what it means by reverses the direction, or the orientation of the particle on the path. Okay, so on the same path here, the path that was generated by this current parameterization right here, we want to come up with a different parameterization, and it's actually a work that within our learning we can actually do. We can be capable of. Okay, so we can come up with a parameterization that we want to just go in the exact opposite direction. Seems like a lot of work, but let me now show you. It's a lot easier than how any one of us here think. Okay, so with our current parameterization right here, and the observation here is that as we change, we always keep t values in the small to large order. If you're going back to my table, that's how it is. It's just for t value, even though being independent, but we will always keep that from going from the low to high. So we want to re-express these so that same order of t values, same order from low to high of t values, but these values here for the x and y will go in the reverse order. That's another way of seeing it. Or you see these points now, for now, with our order of t from 0 to 2.5 right here, it goes like this. But now if we want a different parameterization so that from our t value being the same order here from 0 to 2.5, but our point is going to go this way down. That's the plan. Okay? And so in that way, simpler than anyone will think. All we have to do now is from where our current parameterization, I am going to substitute that with a minus t. Substitute our x of t here with a minus t. And our current parameterization for y here. For our y, I am going to also substitute, instead of t, I am going to substitute with a minus t. Okay? And now your algebra skill is going to be strong enough for you to do, will be comfortable enough, good enough for you to do this. Substituting minus t into your current parameterization for x, we're looking at 2 minus, but now the t here is substituted by minus t. And so this work here will give you 2 plus t now. Okay, and then this next one here will be 3 times negative times minus 3. I mean 3 times minus t, and then minus 1. So altogether it becomes minus 3t minus 1. Okay, and you can see that it's already a different parameterization. It's a completely different parameterization compared to the beginning one. The beginning one was 2 minus t, here is a 2 plus t. It was 3t minus 1, here is minus 3t minus 1. Okay, so the good rule of thumb, and this problem here, if you want to reverse the direction of your particle on the path, on the same path, then the only trick is this: just substitute a minus t into your current parameterization, and it will give you the new set of parametric equations that describe the reversed direction. Okay, so let's see how it happens. So now on my decimal screen right here, okay, the path is still the path. That same path right here. That same path is still here. So what matters now, we don't want the points, we don't want our particle to travel that way up anymore. We want our particle to travel downward, okay, from the left to the right. And so all we do now, just go back and modify this as 2 plus t. Okay, and this is now minus 3t plus minus 3t minus 1. And then of course don't forget to change this as well. All right, so now when t equals 0, we're looking at that point. When t equals 0.5, we're looking at, you see how the point is moving downward this time? So let me move my graphing space so that we can see more motion of the graph. But so that means the next one here will be like that, and like that, and like that. Okay, and observe how my table changes, and observe how these points keep popping out right here. Okay, and if you want to, we can I can also roll back to how about a negative value for t? How about negative 2 right here? Okay, which gives me a point right there, and down to a negative 1.5, okay, and jump to a negative 1, and these are all, I'm speaking in terms of the values for t right here. And so now, obviously, on the same path, but now our particle is making motion in the opposite direction, in the reversed direction. All right, and that's how it is for this kind of example problem right there. Okay. And so, concluding out this this lesson here, this first half of this lesson, it's pretty lengthy already, but I want to give as much detail because I want to build a strong foundation. So when you're gonna be ready to apply your calculus understanding like that, then you won't be surprised at any of the steps like that. But now, another conclusion before we completely leave this half of the lesson here is that it is entirely possible, okay? It is entirely possible that we have two different it is entirely possible to have two different parametrizations, okay? Can give or can have one exactly or exactly the same path. So just now, as I said, the path is just a path. A path is just a path. But just now, right after example 14, you can see this parameterization. X of t equals 2 minus t, and y of t equals 3t minus 1. This is one parameterization. And then later we came to x of t equals 2 plus t. It's already a different parameterization. And y of t equals minus 3t minus 1. These are completely two different parameterizations. But they stay on the same path. They have exactly the same path, and it is entirely possible. And so now when I'm saying two different parameterizations can have exactly the same path, it opens a door that there could be the same path, but we can have even more than two. We can have multiple different parameterizations to generate the same path here. Okay?